Let's solve the tutorial sheet on atomic structure 2025. So the first question is wave calculations, and the first question is sound waves, not EM radiation, travel at 330 meters per second in air. Calculate the wavelength of a 20 kilohertz sound wave. Then the second one, B, is critical thinking. Why can sound exhibit a photoelectric effect like light? Okay, so let's start with the first one. So we are told to calculate the wavelength, okay, of a 20 kilo hertz sound wave. Okay, how do we find the wavelength? So we're going to say the wavelength, that is lambda, okay, is equals to your V. In this case, it's the speed of light, or just the speed, divided by the frequency, okay? This will give us, they've given us a velocity, this is traveling at 330 meters per second in air, okay? Then the frequency, in this case, we've been given 20 kilohertz, okay? You know that frequency is measured in hertz. 20 kilohertz will just mean you're multiplying by 1,000. Okay, so this will be 20,000 hertz. So we're going to divide by 20,000 hertz. Okay, then when you divide the two, what are you getting? On my end, I'm getting 0.0165 meters. Okay, then if you want to convert that to millimeters, this will just be 16.5 milliliters, okay, millimeters, okay. Let me say mm, okay. If you want to represent it in millimeters, okay. Then the second question is, why can sound exhibit a photoelectric effect? Now, what do we know about the photoelectric effect? There should be electromagnetic waves, right? Let me say this is a metal. This can be electromagnetic waves. They can either come from the sun, either from a microwave, okay? Anything that exhibit, electromagnetic waves, okay? Radio waves, infrared, all those kind of things. Now, when they hit a metal, and as they are hitting the metal, above the threshold frequency, photons will start to be released, okay? Photons will start to be released, okay? Electrons will start to be released from that metal. As you are increasing the intensity of the light, so will be the electrons be released like that, okay? Now, for electromagnetic waves, they don't require a medium, okay? Example like radiation, because we're talking about radiations here. So they don't really require a medium, okay? A medium can be air, can be water, okay? They don't require all those kind of things. That's why in this question they've specified not EM radiation. So we're not talking about sound waves which are radiation, okay? But these ones, the sound waves which require a medium. So now, why won't they exhibit a photoelectric effect like light? Okay, one point that you can say is that sound waves are mechanical waves, okay? They are mechanical waves, okay? Mechanical. They are mechanical waves. And you know that mechanical waves, they require a medium. So, for sound waves, they propagate by vibrating particles in a medium like air. Because for you to be able to hear me, I have to say something and a vibration has to take place. Now, that vibration has to take place through a media. An example of a media is air itself, okay? So they'll propagate by vibrating in a medium like air, rather than those ones which are consisting of photons or electrons, okay? And you know that photons are just the quantum particles that are very responsible for triggering the photoelectric effect like we've represented here. Then the other thing is that sound waves are very low in energy, okay? They are low in energy. That is very important to understand, because for sound waves themselves, they depend on the frequency, and energy in this case in terms of waves just given by the Planck's constant multiplied by the frequency. Okay, now the Planck's constant is like 6.63 times 10 to the power negative 34, and you are multiplying that by the frequency, so that would be like very low in energy, looking at just the Planck constant itself. Okay, hope we are good. Let's proceed. We do the next question. Question 2 was about photon energy. Okay, we're saying a microwave photon has a wavelength of 1.2 centimeters. Okay, they've given us a wavelength. Our lambda is equals to 1.2 centimeters. Okay, question 1 is calculate its frequency and energy. B is how does the energy of a red photon compare to that of a blue photon. Okay, let's first start with the first one. We have to calculate its frequency and its energy. Okay, its frequency and its energy. Let's start with its frequency. How do we find the frequency? We say frequency is equals to the speed of light over your wavelength, like that. You remember that C, the speed of light, is just equals to your lambda, your wavelength, multiplied by your frequency or your velocity. Okay, in this case I'll just put it like that. When you make frequency subject to the formula, it will just be frequency is equals to C over lambda, like that. Okay, or your wavelength. So that's what we've put here. So now what is the speed of light? Okay, I'll just put 3 times 10 to the power 8 meters per square second. Okay, that is the speed of light divided by the wavelength that we've been given. Now we've been given 1.2 centimeters. Length or wavelength is measured in meters, so we have to convert this to meters. Okay, so you remember that so what are you going to do? You're just going to you're going to divide this by 100 just for you to get meters. Okay, so you're going to have when you divide that on my calculator, I'm getting 0.012, so this will be meters. So that's what we are going to put here, 0.012 meters. Okay, then we solve. We're going to realize that our frequency will be equals to, on my end I'm getting that is 2.5 times 10 to the power 10. Okay, this is hertz. Okay, the frequency is measured in hertz, so that will be our frequency. Now let's solve the other one. We've also been asked to find the energy. Okay, now the energy, how do you find the energy? Earlier we've said energy is just equals to your Planck's constant multiplied by your frequency. Okay, and let's just do that. Planck's constant is a constant. It is 6.63 times 10 to the power negative 34. Now we are multiplying this by the frequency. We've already found our frequency, which is 2.5 times 10 to the power 10. And when you do your math, on my end I'm finding 1.6 times 10 to the power negative 23 joules. Okay, energy is measured in joules. Okay, so that's how you solve this one. Very simple and very straightforward. You can also try out just to get the concept. Then question B is saying, how does the energy of a red photon compare to that of a blue photon? Explain. Okay, now you remember there's what we call, allow me to rub on, where am I going to rub? Let me just rub this part. Now you remember that from your rainbow or from your spectrum, we got colors abbreviated as ROIG. BeV. Okay, now the question is, how does the energy of a red photon, red, compare to that of a blue photon? Okay, now one thing that you need to understand about these colors, wavelength, when you are starting from this side, wavelength is let me say wavelength and energy. Let me also put this side, wavelength and energy. Okay, so when you are coming this side, the energy will be very high. Okay, here you have low energy. Then in terms of the wavelength, this one would be short wavelength, this one will be okay, so like the wavelength and the energy, then this side you have a longer, wavelength. Yes, okay, so now based on this premise, what are we talking about? So red itself will be low in energy. How is it going to be low in energy? Because it has a very short wavelength. Okay, when you calculate your energy, because you have a short wavelength, you have low energy. Okay, but now on the other hand, red, as you are going this direction, okay, the energy is being increased. Okay, blue light or blue colors will have high energy. Why is it, why do they have how can I say, why do they have high energy? It's because of the wavelength that we've just talked about, and energy is direct proportional to the frequency of these waves. Okay, that is worth mentioning. Then question C is a critical thinking question. If wavelength doubles, how does the energy change? Explain conceptually. Okay, now how do you explain C? So if you double the wavelength, you remember if we say speed of light is equals to the wavelength multiplied by the frequency. If we make the wavelength the subject of the formula, so we have wavelength is equals to speed of light over frequency. Now you are able to see that your wavelength is indirectly proportional to your frequency. Okay, that is very important to mention. Your wavelength is indirectly proportional to your frequency. Now because of this relationship, you'll be able to see that if the wavelength is doubled, if we double this wavelength, okay, frequency on the other hand will be halved. Let's say we double it by 2. On the other hand, the opposite of 2 will just be 1 over 2. So the wavelength, the frequency will be halved, and because of this, you know that energy is proportional to frequency, so the energy will also be halved. Okay, the energy will also be halved. Right? Because energy itself is proportional to frequency. Your energy is proportional to the frequency. Now because the frequency has been halved, so your energy will also be halved. That's what we're talking about. Okay, very, very important. So that's the relationship that you need to understand. Okay, that is very important to mention. Then question D is saying allow me to wrap this part. Okay, question D is, radio station WCBS in New York broadcasts its FM radio or FM signal at a frequency of 1 point. Okay, so the FM or the frequency modulation, you might want to say that this is at a frequency of 101.1 megahertz. Okay, and their AM signal, okay, AM, that is the amplitude modulation, is broadcast at 880 kilohertz. What are the wavelengths? Okay, what are the wavelengths of these signals expressed in meters? Okay, so that is our question. So let's start with FM. How are we going to find the frequency or the wavelength? We said wavelength is just equals to the speed of light over the frequency. The speed of light, we've said, is 3.0 or 3 times 10 to the power 8 meters per square seconds, okay, divided by the frequency of FM we've been given is 101 that megahertz. Now mega, we know that mega is just a million. Okay, so what are we going to do? We're going to say 101.1 megahertz, we've said, is a million, so that is 10 times 10 to the power 6. A million is 6, right? Hertz. Okay, I've changed the megahertz to a hertz. Okay, then what are you going to do? You just do the mathematics. You divide the two. What are you going to get? On my end, I'm getting 2.97 meters. Okay, so that would be the wavelength for the frequency modulation. Okay, then what about for the amplitude modulation? We are saying the wavelength is equals to the speed of light over the frequency. The speed of light, that is 3 times 10 to the power 8 meters per square second. This is dividing by the frequency we've been given is 880 kilohertz. Okay, so I'll write that 880. Now we are saying kilo is 1,000, right? So I'm going to say times 10 to the power 3. This will be hertz. Okay, and when we divide, on my end I'm getting 341 meters. Okay, so that would be the answer for the amplitude modulation. Now let me make something clear here. If you have your wave, let me say this is your wave. Okay, the frequency is how many times the wave is repeating itself. Okay, it's how many times the wave is repeating itself. The amplitude is how high. Okay, the amplitude is how high. So when I'm talking about FM signal, it means such a signal that is based on how many times the wave is repeating itself. Then the amplitude will be based on how high the wave is, like in terms of magnitude, how high the wave is. Now one thing that you should know here is that for the frequency, these ones, at least they adapt. They don't have they don't make a lot of noise. But for the amplitude, these ones, they usually make a lot of noise here and there. But it depends on what you're using. But now this radio station, they are WCBS in New York. They're able to broadcast both using FM signal and AM signal. Okay, then we've got another question. Question C says, calculate the energy and the wavelength of a photon of light with a frequency of that. Okay, that is very simple as well. So let's just do that. Okay, what are we going to have if we do that? So we're calculating the energy and the wavelength. We're calculating two things here. You have to note, we're calculating two things: energy and the wavelength of a photon of light. So that is E. So how are we going to find the energy? Let's start with the energy. So the energy, we've been saying that is just the Planck's constant multiplied by the frequency. Okay, so when you substitute the Planck's constant, that is 6.63 times 10 to the power negative 34, yeah, like that. We are multiplying this by the frequency. They've given us the frequency, it's already in hertz, so I'm just multiplying. Very simple. 6.165 times 10 to the power 14 hertz. Okay, so what are we going to have? What are we going to have? On my end, I'm getting 4.09 times 10 to the power 19, negative 19 actually. Okay, that's what the calculator is showing, negative 19. This is energy, so it's measured in joules, so I'll put the joules like that. Okay, now how do we find the wavelength? So we're going to say the wavelength, which is lambda, right, will just be, we've said it's the speed of light multiplied by the divided by the frequency. The speed of light divided by the frequency. Okay, the frequency is just there also, you just put your values. They've given us everything. Then on my end, I'm getting, when I divide, I'm getting 4.87 times 10 to the power negative 7, because this is the wavelength, is in meters. Okay, okay, I'm just ignoring the side, the units, okay, because of space. Then F, we are saying element Y emits a blue photon with a wavelength of 4 point that. Okay, so element Y emits a okay, finding F, we're saying element Y emits a blue photon with a wavelength of 4.8 times 10 to the power negative 5. Calculate the energy of the blue photon in joules and in electron volts. Okay, let's start with the energy in joules. Okay, how do we find the energy? We've been saying it's Planck's constant multiplied by the frequency. Okay, multiplied by the frequency. Now, are we given the frequency? No, we've been given the wavelength. So we're going to manipulate our formula. We remember that frequency, speed of light, is just equals to wavelength multiplied by your frequency. Now, if you make frequency substitute the formula, frequency will be equals to your c over your lambda, like that. Okay, so we're just going to replace the frequency by that. So we have h multiplied by c over lambda, because that's what we are given. So we're going just to replace now. We're going to replace, allow me to wrap this part. Okay, we're going to replace, and what are we going to have? Planck's constant, we've just said, is 6.63 times 10 to the power negative 3, 4 on that 4. This is multiplied by the speed of light, 3 times 10 to the power 8, everything over the wavelength. We've been given a wavelength of 4.8 times 10 to the power negative 5 centimeters. Okay, that is in centimeters. So what are you going to do? You have to convert it to meters. Okay, so you have to divide that by 100. Okay, when I divide by 100 on my end, I'm getting 4.8 times 10 to the power, instead of negative 5, I'm having negative 7. This is in meters. Okay, now when I solve this one on my end, 3, the speed of light divided by 4.8 times 10 to the power, okay, the answer multiplied by 6.63 times 10 to the power negative 4. Okay, so on my end, I'm getting 4.14 times 10 to the power negative 19 joules. Okay, this is energy, so it's 19 joules, like that. So we found the energy. Now the other question is, we have to find the energy in joules and in electron volts. Okay, now how do we find the energy in electron volts? Now, in electron volts, it has a conversion factor. 1 electron volt, this is equals to 1.6 6 times 10 to the power negative 19 joules. Now, what if now we have 4.1, the energy that we've just found, times 10 to the power negative 19 joules? What would be the electron volts? Okay, let's just put X there. So just going to cross multiply. So what would be our answer? Okay, let's just do that. What would be our answer if we just cross multiply? We have 1.6 times 10 to the power negative 19 joules. X is equals to 4.14 times 10 to the power negative 19. So we're going to divide by 1.6 times 10 on both sides to just get your X, okay? Times 10 to the power negative 19 on both sides, okay? So your X, in this case, on my end, I'm just getting 2.59 electron volts, okay? So that would be our answer in electron volts. Okay, let's go to the second question. We're done on this one. Question number 3. Photon emission. We are saying copper 1 chloride in fireworks emits blue light with that wavelength 450 nanometers. Calculate. We're trying to calculate the energy per photon. Okay, energy per photon. Let's start with the first one. We're saying we calculate the energy. Energy, we've been finding energy. Energy is just equals to your Planck's constant. Are we given the frequency? No. We've been given the wavelength. Okay, so we're going to say C over the wavelength. Okay, that is just the same as frequency. So now what do we do? Okay, we just replace now. So our Planck's constant, that is just 6.63 times 10 to the power negative 34. This is multiplying by the speed of light, 3 times 10 to the power 8 meters per square second, divided by the wavelength. The wavelength we've been given 450. Now nanometers, you have to convert that to meters. You know that nanometers, that's just 10 to the power negative 9. So I'm just going to replace, to put 10 to the times 10 to the power negative 9, and it is in meters. Okay, then you do your math. Okay, so I'll just do everything together. I'm finding my energy as 4.42 times 10 to the power negative 19. Now we're talking about energy, so this is in joules. Okay, so that will be our energy. Okay, then that is the energy that will be released per photon. Okay, so the energy per photon will be 4.42 times 10 to the power negative 19 joules. Okay, now let's go to B. B is what does reg BeV represent on the electromagnetic spectrum? Okay, like I earlier said, I was talking about reg BeV. Okay, so this is just an acronym for the colors that will be visible on the spectrum of light. Okay, so R just represent, okay, reg BeV like that. R represent red, O orange, Y that is yellow, green, blue, indigo, and violet. Okay, that's just that. Okay, so these colors are in order of increasing frequency, like I showed you. Then increasing frequency, that is to mean you are decreasing the wavelength. Okay, from the one with the highest wavelength to the one with the lowest wavelength. Like for example, red it being the first one, it has the longest wavelength. And at the same time, because it has the longest wavelength, because red has the longest wavelength, it will have low energy. Okay, then on the other hand, this will be the highest wavelength. They'll be high in energy. Okay, high in energy as you are going in this direction. That's why we came up with this they came up with this acronym reg BeV. Then C is critical. What is C? Okay, Okay, I think there was a typo here. It's BB, but it's just supposed to be C. Okay, so C say it's a critical thinking question. Why do different metal salts produce different or produce distinct colors? Okay, why do they produce distinct colors? Okay, so this you're just trying to explain here. You know, different metals or metal salts, it can be copper sulfate, copper chloride, as long as it's a salt but it has a metal in it. Barium sulfate, okay, all those kind of things, they are salts. But why do they produce distinct colors? So the reason is that different metals will emit distinct colors because they have unique arrangement of electrons. The way electrons are arranged in these metals, they are really different. You know, for copper, it's really different. We're talking about what do you call this one? The quantum mechanical model of atoms. Okay, we're using the Pauli's exclusion principle, Hundi's rule, all those rules into consideration. We saw that the electrons are arranged differently. Okay, so when these salts are heated, one thing that you should know is that their electrons absorb energy and move to high energy levels. Okay, so let me say this is these are the shells. We have the nucleus in the middle. Okay, when you hit these let me say metals, maybe copper or whatever. So example, this electron, because there are a lot of, these are energy levels, they're also called shells. Okay, this electron can move to, this is n1, n is equals to 1, this is n is equals to 2. When they are heated, this electron gets excited and it can go to the second energy level. Okay, when you heat it. But now the excited state, we call that the excited state. When they have high energy like that, in the excited state, they don't stay for long. Okay, within a short period of time, again they'll get back again to where they were in the first shell. That's what we're talking about. Okay, so when you hit these ones, the electrons absorb energy and move to higher energy levels. The electrons will return to lower energy levels. Now when they are returning, they release energy as light. Okay, so they release energy as light. When these electrons are returning, they release energy as light, and that light, it can be in different colors. Okay, and the energy emitted will correspond to a certain wavelength, to a specific wavelength. Okay, and in different wavelengths, there are different colors that are based on the element's unique electronic structure. Okay, copper to be something like green. Okay, barium in the lab, it's also like green, like that. Okay, sodium would be something like yellow, all those kind of things in the lab. Okay, so that's what I'm talking about. Now question number D is, can two different elements produce the same emission spectrum? No, we've said they've got unique arrangement of electrons. So two different metals cannot produce the same emission spectrum. Why? Because each element has a unique set of energy levels that we've talked about, and the transition between these energy levels results in characteristics of the spectrum which are different. And this is why emission spectrum, sometimes they are also called what we call fingerprints. Okay, your fingerprints, they are different to someone's fingerprints. Okay, so even these ones, they are just like different, very unique. Number E is, one of the lines in the spectrum of mercury produced in a mercury vapor lamp is green and has a wavelength of 540 nanometers. What is the frequency of this line? Okay, what is the frequency of this line? Okay, this is also a simple question. We've been solving these ones. What are we going to say? That is E. How do we solve E? Allow me just to rub here. Okay, so we are saying this is green and as a wavelength. So they've given our lambda as our wavelength, which is lambda. It's 540 nanometers. Okay, then they're asking us to find the frequency. Very simple question. So what are we going to do? We're going to say our frequency will just be equals to when you make frequency a subject of the formula in that regard, we're saying it's the speed of light divided by your wavelength. Okay, the speed of light, that is 3 times 10 to the power 8. I'll not put the units, that is meters per square second, divided by the wavelength. They've given us the wavelength 540. Now this is in nanometers. You convert it to meters. Okay, you're converting it to meters. What are you going to say? Nanometers, we've said, is times 10 to the power -9. Okay, and you just solve like that. What are you going to get as your frequency? That is on my end, I'm just getting 5.56 times 10 to the power 14. This is in hertz. Okay, those are the units for frequency. So this would be the frequency, how the cycles per second. Okay, the cycles per second of this wave. Okay, then question, is it question F? It's saying calculate the frequency of light that has a wavelength of 4.25 times 10 to the power -9 meters. Identify the type of electromagnetic radiation. Okay, this is very, very interesting. Okay, so let's solve that one. How are we going to solve this one? Calculate the frequency of light that has a wavelength of that. Okay, so we're calculating the frequency. So it's the same thing. Frequency will just be equals to C over lambda, like that. 3 times 10 to the power 8 over the wavelength. The wavelength they've given us is already in meters, 0.25 times 10 to the power -19. It's already in meters. Okay, when I do the math on my end, I'm getting 7.06 times 10 to the power 16 hertz. Okay, so this is the frequency. Now that we found the frequency, we're taught to identify the type of the electromagnetic radiation. Okay, the type of the electromagnetic radiation. So how are we going to do that? Okay, the type of the electromagnetic radiation. So this wavelength that we found, a wavelength, they've already given you a wavelength, so you just have to know where are you going to find this wavelength. Where are you going to find this wavelength? So you check on your on your electromagnetic radiation spectrum. The wavelength, though, 4.25 times 10 to the power, it falls in the X-ray region. Okay, X-ray region, okay, of the electromagnetic spectrum. Okay, so you can either check them here and there. So this will just be in the X-ray region, like that. Okay, let's solve another question. The photoelectric effect. Earlier we've introduced the photoelectric effect. Okay, question A. Let's go direct to the questions. Explain how the photoelectric effect supports quantization of energy. Okay, just to again polish it up. This is a metal. Light is coming. Okay, this can be sunlight. We know that light has a lot of things. You have infrared light. There's a visible part of light. There's the microwave. All those they are like components of that light. Okay, so those ones are electromagnetic radiations. Okay, so they are coming and hitting this metal. Okay, hitting this metal. But now, when you bypass the threshold frequency, electrons will start to be ejected. Okay, or what we call photons. Okay, photons will start to be ejected. But now, how will photons be ejected? Because you've crossed the threshold frequency. Now let's say the threshold frequency was at 20. Okay, now you've increased your intensity of light to 30. You have maybe ejected 10 photons. Now let's say you put it at 40, so meaning 20 photons will be ejected. Let's say you increase the intensity at 50. Okay, let's say 30 photons will be ejected. What am I driving at? You are able to see that as you are increasing the intensity, even the quantity of the photons to be ejected are increasing. Okay, so what's the conclusion then? Electrons are only ejected if the light has enough energy. Okay, this energy will correspond to the photon's energy, showing that energy will come in fixed amounts. Okay, it will be in fixed amounts. Then on the other hand, these electrons are being ejected. Being ejected, it means they have kinetic energy. So what can we relate now to in terms of the frequency? So the higher the light's frequency, the more energy the photons will have. Now when the energy is so high, this will now in turn increase the kinetic energy of those ejected electrons. Okay, that is worth mentioning. Then the other thing is that electrons absorbs this energy from one photon at a time. Okay, proving that energy is delivered in chunks like that, or in quantities, what we call now quantization of energy. So that's how you go about that one. Let's solve B. B is rubidium. Works function is that. Okay, that's the work of rubidium. We are told to calculate the kinetic energy of electrons ejected by 254 nanometers of light. Okay, so okay, so how are we solving this one? Let's start. Okay, let's put what we have. We've been given the work. The work of rubidium is 208.4 kilojoules. Okay, now to find the energy needed for one electron, what are we going to do? We're going to divide by the Avogadro's constant. Okay, we're going to divide by the Avogadro's constant and that and whatever. Okay, so what should we now do? Let's solve it. So we are going to say the energy. Let's find first the energy, because I don't find the kinetic energy. Let's find the energy. So the energy of a photon, we know that is just Planck's constant multiplied by your the speed of light divided by the wavelength. I've not put the frequency because we've not been given the frequency, but at least we've been given the wavelength of 254 like that. So we're going to use that one. So let's find the energy. Planck's constant, we've been saying, is that is just 6.626 times 10 to the power negative 34. Okay, this is multiplied by the speed of light, 3 times 10 to the power 8. This is divided by the wavelength. We've been given 254 nanometers. I've said just 10 to the power negative 9. We will convert it to meters, just be meters like that. Okay, now when we do the math on my end, I'm getting the energy to be 7.83 times 10 to the power negative 19. This is the energy. So this will be joules per photon. Okay, because they've asked us to calculate the energy ejected, calculate the energy of kinetic energy of electron ejected by the light. Okay, so this will be the energy, 7.83 times 10 to the power negative 19 joules. Okay, then what do we now do? Okay, so this is the energy. Then calculate the maximum kinetic energy of electrons ejected by 2. Okay, so we've just found the energy, but now this electron also has a work function, or how can I say it? This metal rubidium has a work function of 208. That's a work function. So what are you going to now have as the maximum kinetic energy of those electrons that will be ejected? Okay, so you know that from your law of energy is neither is neither destroyed or created. It is just converted from one form to another. So what are you going to do? So we're just going to subtract the 2. Okay, we've been given 204 like that. Okay, what do we now have? Okay, anything that we've been given here? Nothing. Okay, so that's the energy of the photon. Then let's go to C. Apparently C is saying it takes 7.21 times 10 of energy to remove an electron from a sodium atom. What is the maximum wavelength of light that can do this? Okay, so what are we going to do? So we are finding the maximum wavelength of light. Wavelength, if we make wavelength substitute the formula in this expression, what are we going to have? We are going to have wavelength will just be equals to the Planck's constant. This is multiplying by C. Your energy will be there down. Okay, it's like you're just cross multiplying. So let's just do that. We've been given everything. The Planck's constant is 6.626 multiplied by 10 to the power negative 34. This is multiplying by the speed of light, 3 times 10 to the power 8. Okay, divided by the energy. We've been given the energy, it's already in joules there, so just replace it there. 7.21 times 10 to the power negative 19 joules. Okay, so what do you find as your wavelength? Okay, so on my end I'm getting 2.76 times 10 to the power negative 7. Okay, this is in meters. Okay, you can either leave it in meters, but most of the times you've seen that most of the time we are leaving our answer, or most of our questions are coming in nanometers. So I can compare this one to nanometers. So what are you going to do? What are you going to do? You're going to multiply this expression by what? By 10 to the power negative 9. 10 to the power negative 9. So in the end you have just 276 nanometers. Okay, so that would be your answer like that. Okay, and to access all the solutions, everything will be uploaded on our drive. Thank you.